All right, what's grouped together over here? What numbers? 2 and 3. All right, what's grouped together over here? 3 and 4. So you've got to follow your order of operations. So you've got to do parentheses first. So this would force you to add the 2 and the 3 first, and you get 5. Well, then 5 plus 4 is what? 9. Now over here, you're forced to add the 3 and the 4 first, which gives you 7. And 2 plus 7 also gives you what? 9. Now, sometimes you make up things that aren't true in your head. Like if I ask you this. And I said, what property is that? What property is that? It's commutative property of addition. It can't be associative property of addition. Because over here you got the 2 and the 3 grouped together, and over here you got the what? The 2 and the 3 grouped together. You didn't change the grouping. What you changed was the order. You said 4 plus this parenthesis is the same thing as this parenthesis plus 4. So sometimes kids make up shortcuts that do not work. So if the only time you ever showed commutative, it did not have parenthesis, and every time you showed associative, it did have parenthesis, they're going to think when they see a parenthesis that it's associative property, and it's not necessarily. So you got to be real careful when you're doing properties. Now, properties are not something that you teach one time and then you're done with it, okay? You should teach properties every time that you do something. So when you do something on a test, sometimes I'm going to ask you what rule said you could do that, and you got to tell me what property that is, and we're going to do it the rest of the semester. So you've got a lot of properties of addition that we went over, okay? Now, they're not any properties of subtraction. Now think about why. What do your whole numbers start with? By the way, what do whole numbers start with? 0, very good. What numbers start with 1? Because I'm going to ask you that on your test next week, probably. What group of numbers is this?
Counting.
All right, there's 2 ways of saying that. One is called counting numbers. What's another phrase that means the same thing that we talked about? Natural numbers. So I would expect you to know both of those. Okay? So all the properties, since counting numbers are part of this set, they're a subset of this. All these properties work with whole numbers or with counting numbers. Now they're also going to work with integers and real numbers and rational numbers and numbers we're going to get to later. But right now in kindergarten, they start with whole numbers. Okay? Now the first numbers kids ever encounter are counting numbers. You know, their mom will say, "Would count to 3 for your grandmother." You know, 1, 2. They don't start with 0. They start with 1. That's how you count. Then when they get to kindergarten, they find out there's a symbol that stands for nothing. Okay, and that's a pretty big deal when you're 5. All right, so their world gets a little bit bigger, and they find out there's actually a set called whole numbers. Now, closure property. Remember what closure property means? When you put things together in the set, the answer's got to be in the set. All right, so like Amber said, there's a closure property for addition of whole numbers. Because if I take 2 and 2 and 2, if I take 2 out and add it to itself repeatedly, 2 plus 2 plus 2, what's that answer? Is that a member of this set? Yeah. What if is 10 in that set? Is 100 in that set? What's 10 plus 100? 110. Is that in that set? Yeah. So this set's closed under addition. This set is not closed under subtraction. Now, I might ask you why on a test. Show me why that set's not closed under subtraction. That means you got to find me at least one time it doesn't work. Okay? So when's the time that when you would grab two things in there and subtract them, the answer wouldn't be in the set? Yeah, like what? Like give me an example.
1 minus 5.
All right, Evan said 1 minus 5. Now what's 1 minus 5? And that's not in that set. So that set's not closed under subtraction. Okay? Now, there's a commutative property of addition. All right, like Amber said, 3 plus 4, 4 plus 3, same answer. Is there a commutative property of subtraction? Is 2 minus 3 the same thing as 3 minus 2? Not in my checkbook. I wish it was, but it's not. Okay? So there's not a commutative property. There's not an associative property of subtraction. Now, what bothered me as a child was there's not an identity property of subtraction. And I remember asking the teacher why. I mean, last time I checked, 5 minus 0 was what? Was 5, right? All right? But why isn't it? Abby, what did you just say? Why is there not one?
Because you can't take 5 from 0.
That's right. In other words, remember what I told you about the identity property? I said any number like A, any number plus 0, or 0 plus any number equals 2. Is everybody with me? Well, it's true. 2 minus 0 does equal 2, but it doesn't equal what? So that's why there's not an identity property of subtraction. So there are not any properties of subtraction. They're properties of addition. Now, similarly, what you need to start with right now is their properties of multiplication. All right, so let's write those down. All right. All right, so these are our properties of multiplication. Now, your book keeps talking about the whole numbers because that's the only set they're talking about right now. Like they're not talking about decimals and fractions and negative numbers, but all these properties are going to work with those numbers when we get there. All right. There is a closure property of multiplication. Okay. So there's a closure property of multiplication. All right. So what do you think that would mean? That a whole number what? Times a whole number is going to equal another what? So a whole number times another whole number is going to equal another whole number. 2 times 11 is 22, and that's a whole number. 0 times 5 is 0, that's a whole number. 100 times 100 is 10,000, that's a whole number. All right? Now let me ask you this. Didn't you have an identity property of addition? Do you have an identity property of multiplication? Now remember what I told you last time about identity. When you hear identity, I want you to think you get the same thing back that you started with. So is there a number that you can multiply other numbers by that leaves it the same? What is it? Is it 0? Is 0 for addition? Is it 0 now? What is it? 1. So, you know, your example would be, you know, if you had like 5 times 1, or if you had 1 times 5, that answer is still going to be what? 5. So you can't just say the identity is 5. Excuse me, the identity is 1. The multiplicative identity is 1, but what's the additive identity? It's what? 0. So you've got to be clear with kids about, is this the identity for addition or is this the identity for multiplication, because the value changes on here. All right. Now, similarly, you have a commutative property of multiplication. All right. So when I say commutative, what changes on commutative? Is it the grouping? What changes on commutative? Like if I'm talking to a 6-year-old, what am I going to tell them you can change? Because I may ask you that in your test next week. What can you change without changing the answer according to the commutative property? The order. You can change the order without changing the answer. So it's a big deal when you're in 3rd grade when you find out that 4 times 9 is the same answer as 9 times 4. Now, 1,000 years ago, when they weren't as smart as they are now, all right, I had to memorize my multiplication facts. And so they gave me a little green cardboard card that had 1 times 1 all the way to 12 times 12 on it. And my homework was to memorize those. So we'd have to memorize the 1s for 2 or 3 days. And then we'd have to memorize all the 2s. And we'd memorize all the 3s. Now, I was always a little bit of a strange child, so I had to go to my grandmother's house after school. So I did my homework as soon as I got there. So I can remember sitting on my grandmother's couch, and I would not let myself off the couch until I got all the ones right for that night. So if that was the day that we were doing the 4s, then I would start with 4 times 1 until I got 4 times 12, and I could get them all right without looking at the card. And sometimes that took a little bit of time, and sometimes I was on that couch a long time. I can still remember the day I was doing the 6s. So like I'm 10. I'm sitting on the couch, I guess I was 9, sitting on the couch, going 6 times 3 is 18. 6 times 3 is 18. 6. I already know that. Now, it's a little sad it took me to the 6s to figure that out, but I glanced up there, and sure enough, 3 times 6 was what? 18. And 6 times 3 is 18. And then I double checked. 5 times 2 and 2 times 5. Like, I figured the property out before they told me the property, and I was so excited because I was going to be off that couch in like half the time. Because I already knew they're my 5s. So now we have half to go. And then I realized by the time I get to my 12s, I'm golden. I just have to memorize one new thing. So it is very powerful for a child. When they're in kindergarten, that commutative property of addition is very powerful because they tend to count with their fingers. So when you tell them to do 2 plus 7, most of them start with 2. Everybody with me? And then they add what? 7. But it is very powerful when they realize they could have just started with what? 7 and added what? 2. So when you're 5 or 6, that is a very enlightening, very wonderful truth that you figure out. It saves you time. It makes flexible. I can either start with 2 and add 7 or start with 7 and add 2. I get to pick. So it's the same way here with this commutative property of multiplication. Now, there's also an associative property of multiplication. Okay, an associative property of multiplication. So what do you change on associative? You don't change the order. What do we say you change with associative? The grouping. So in other words, it would be something like this. If you did 2 times 3 and then said that answer times 4, do you get the same thing if you say the 3 times the 4 first? And then you say it times 2. So here I've grouped the 2 and the 3 together, and here I've grouped the 3 and the 4 together. Notice I did not change the order. Well, 2 times 3 is 6, and 6 times 4 is 24. Well, 3 times 4 is 12, and 2 times 12 is also 24. So I can change the order, and I can change the grouping, and still not change the answer. Now, let me warn you about something. What you don't want to do to a kid is this at the beginning. You don't want to give them a problem like that and ask them what property. What did you do there? Did you change the order? Yeah. 2's first here. What's first here? 3. What else did you change? You changed the grouping. The 2 and the 3 were grouped together here, and what? The 3 and the 4 were grouped together there. Now later, I will give them an example that's got more than one property, but not at the beginning. Because if they miss that, I don't know what they did not see. So they'll change the order when you're changing just the grouping. See, on your example, you've got the 2 first, the 3 second, and the 4 third. So make sure that when you start moving things in groupings, that you don't change the order when you're illustrating associative. So on this one, the directions would say what properties, singular, or properties, plural, have been used. And I'll expect them to tell me, well, the order's changed, so it must be commutative property of addition, and the grouping's changed, so it's also the associative property of addition. They have to tell me both of those. So we have to work our way kind of up to that. Now, isn't there a cool fact about 0 when you're multiplying? What's 0 times anything? 0. That's called your 0 property of multiplication. And so what that says is, any number 4 times 0 or 0 first times any number is going to give you 0. Now it's easy for them to get confused because there's a 0 that shows up in those addition properties. But that's what property has 0 with addition? That's not what? Which property is that? Your identity property of addition. So they get confused because zeros pop up places, that pops up places. Now, here's another one that you need to learn. All right, it's called the distributive property of multiplication over addition. All right, the distributive property of multiplication over addition. Now, here's you an example of it, and I'll write it kind of in general terms. If you had 2 times 6 plus 4. Now, with your order of operations, what do you got to do first here? You got to do parentheses, so you have to add first and multiply second. But the distributive property gives you permission to change that. That's the same thing as 2 times 6 plus 2 times 4. So here I add and then multiply. Here I multiply and then I add. And you get the same answer when you do that. So, in general, it'll be like A and a B plus C is AB plus AC, if you like kind of general things. Now, there's also a distributive property of multiplication over subtraction. So it would work if you had 2 times 6 minus 4. You could say that's 2 times 6 minus 2 times 4. So it works whether you have a plus in the parentheses or whether you have a minus in the parentheses. You either have the distributive property of multiplication over addition or you have the distributive property of multiplication over subtraction. Now, let me tell you what happens sometimes in elementary school that does not need to happen. And it's not just elementary school, it happens in high school too. There's no such property as the distributive one. Don't call it that. There's a distributive property of multiplication over addition. I know that takes longer to say. And there's a distributive property of multiplication over subtraction. I know that takes longer to say. But sometimes what happens is teachers are trying to be, I guess, teacher-friendly, user-friendly, student-friendly. I don't know what the word is. But it hurts them later. And here's the reason it hurts them. When my son was in junior high, he was working homework at the table. You know, when your mother's a math teacher, they're just awful. So he's working this problem. And I don't remember, the problem was something like this. And here's his answer. And I said, Michael, how'd you get that? He goes, it's right. I said, I didn't say it wasn't right. I just asked you how you got it. And he said, distributed property. And I said, there's no such thing. He said, yes, there is. And I said, no, there's not. I said, there's a distributed property of multiplication over addition. I've heard of that one. And there's a distributed property of multiplication over subtraction. That's a real property. But there's not a distributed property of multiplication over multiplication. You see, somebody in his lower grades told him that distributed property meant that something outside of a parenthesis got passed to everybody on the inside of a parenthesis. And see, this structure looks like this structure. So you see what he did? He went 2 times 3, everybody with me? And then he went times 2 times what? 4. And that's not the way you work that problem. So you can't just say, see, there's no distributed property of multiplication over multiplication. So because he was not taught the property names correctly, it bit him later. Now, if the problem had been written like this, he never would have worked it incorrectly. But that form looks like that form. And he just remembered something outside the parenthesis gets passed to somebody on the inside. So you can't phrase things in what you think of to be easier ways if they're not correct. So there's a reason they're called the things they're called, and there's a reason we say them the way we say them. It's because if we don't, it's going to cause a problem later. Now, you've got to know all of these properties for your test next week. So you've got to know all the properties of addition and all the properties of multiplication. I may give you a property and say, make me up an example. Or I may give you an example and say, what property does that illustrate? So you got to be able to go both ways. Now, there are not any subtraction properties and there are not any division properties. Because think about it. When you divide 2 whole numbers, do you always get a whole number? 2 divided by 4 is a half. That's not a whole number. There's no commutative property of division. 2 divided by 4 and 4 divided by 2 don't give you the same answer. There's not an associative property. There's not an identity property. So the properties that you have to know are the properties for addition and the properties for what? Multiplication. Now, what I want to talk about next are what we call models. All right, I want to talk about how do you teach kids to add, subtract, multiply, and divide. Because that's going to be your job. All right, so the first thing kids learn to do is they learn to add. Okay, so let's go talk about models for addition. Model. Now, I know that you know the answer to 2 plus 3, or we got a big problem. All right, you're in college, so I know you know the answer to 2 plus 3. The problem is you're going to have to be able to teach a child how to figure out what 2 plus 3 is. Now, in your books, they're kind of starting on page 98. You kind of like following your books. Now, here's what you're going to do every time when you teach. No matter what subject, no matter what grade. You have to start totally concrete and then gradually move them to abstract. So you don't usually jump from concrete to abstract, and you sure don't start with abstract. So the first model that you're going to use for addition is the Sept model. So if you're the kindergarten teacher, here we go. Now that's why we had to go over sets. Now, the definition for addition, they give you on page 99. It says, let A and B be two disjoint finite sets. Remember what disjoint means? Disjoints means they don't intersect. They've got no overlap. All right? Then the cardinal number of A, the A plus B is when you're doing the cardinal number of the union of two sets. Now, what do I mean by that? I mean, if I want to teach a kid to do 3 plus 2, then I'm going to go to them and I'm going to give them some manipulatives. It might be Skittles, it might be base 10 blocks, it might be beans, I don't care what it is. But I'm going to have 3 things in one set. And then I'm going to have 2 things in a different set. And I'm going to tell them, I've got 3 things in this set, and I've got 2 things in this set. And I'm going to use proper terminology. I'm going to tell them we're going to union the sets. Now, is union all of it or what they have in common? What's union? All of it. So they're literally going to stick those 2 sets together. And they're going to count how many is in those sets, in that new set. And when they count 1, 2, 3, 4, 5, you understand the cardinal number for the first set was 3. There were 3 things in the first set. The cardinal number for the second set was 2. There were 2 things in that set. And then they literally physically union those sets and count the cardinal number. Now, for a test, it says I can't have you more than 6 feet from me. What you're going to do is have to draw it. All right, so if I said illustrate 3 plus 2 using the set model, then you've got to show me that you had 3 things, I don't care what they are in one set, and then you had how many in the other set? 2, and then you got to tell me that you union. And then I got to see what you think that's going to look like. So that's 3 things plus 2 things give me what? 5 things. And we're going to do it over and over and over with Skittles or beans or whatever. I'm going to have 4 things plus 9 things, and we're going to union them. I'm going to have 1 thing plus 7 things, and we're going to union them. Then we're going to do 7 things plus 1 thing and union them. So they're going to figure that commutative property out before I ever tell them. It's way more fun when they figure things out for themselves. And then later we name what they've already figured out. So that's completely concrete. Now, I don't want them having to have Skittles when they're 17, okay? So I've got to gradually move them. When they get very good at the set model, the next model that I'm going to use with them is something called number line model. Now, if they're in kindergarten, first grade, do they have any negative numbers? They don't have any fractions. So their number line starts with 0. Now, here's what I mean by you've got to gradually move them from completely concrete to abstract. I probably would go to the school supply store, you can do it online, and get basically a measuring tape, so to speak, that's a sticker that will go across the top of their desks. It would go from 0 to 20. Everybody would have one on their desks. Then I'd probably go over to the Dollar Tree and buy some packages of little micro cars for $1. Now what happens is, if you're going to illustrate 3 plus 2 on the number line, this first number tells you where you start. So where am I going to start? On what number? 2, 3. So they got their car. They're ready. Now when you're adding, which direction are you going to move? To the right or to the left? To the right. And this plus tells you to move to the right. This second number tells you how many moves to make. So this first number tells you where to start, and this second number tells you how many places to move. So they're sitting there on their car and they go to the right, one what? 2 spaces, and that's where they stop. And their answer is where they stop. They'll drive that micro car all day. We're going to do 7 plus 5. You see what I'm saying? Like, this is way more fun. Now, understand what I'm doing. I'm doing a mixture of concrete and abstract. Now, we're going to drive those micro cars for days because it's fun. Gradually, I'm going to take the cars away. And now they're going to use their finger. They're going to start at 5 and go to the right 4, or they're going to start at 1 and go to the right 9. Is everybody with me? Now, do you see, that's a little more abstract than the car. Later, I'll take the number line off, and they're going to have to draw it. So do you see what I'm doing? I'm gradually moving from concrete to what? To abstract. But giving a kid this isn't a model. That's just completely abstract. So we're not going to get to that for a long time. So you don't just teach beans one day and then give them a speed test for this next week. They're going to freak out when you do that. Now, you need to understand that in math, that the goal is accuracy. Speed will come. And you got to pick your battles. And what I mean by you got to pick your battles is this. I have a PhD and I count on my fingers. It just makes me feel better. My children count on their fingers. So when my son was in 2nd grade, they had a math bee every Friday like people have spelling bees. She's trying to get them to do addition facts really quickly at the beginning of the year. Michael Gann won every week. If she told him 9 plus 8, he's 17. Now, I adored his 2nd grade teacher. I requested her because my daughter had her name, and so I requested Miss White. She was fabulous. But Miss White did not like you to count on your fingers. So she told Michael, you can't count on your fingers anymore. Yes, ma'am. So the next Friday when he gets up, he has on a long sleeve jacket. Where are his fingers? Up in the what? Yes. The jacket. She's like, Michael, push those sleeves up. So he pushed his sleeves up. You know what he does next? He puts them right here. And what's he do? Unless you're going to cut my baby's hands off, he's going to use his fingers. Now, it would be different if it was hurting him. You see what I'm saying? But is it hurting anything? No, he's getting the right answer and he's getting it fast. Why do you care? I know some teachers that want the children to show the numbers that they carry. We'll talk about that later. Why? Why do you care? Now, if it's causing trouble, then do something about it. But if it's not causing trouble, what? Leave it alone. Okay? You got to pick your battles. So I want kids to know it's better to be right than to be fast. Because when you try to make them fast first, their anxiety goes up. I mean, do you remember being freaked out by timed tests? Has anybody ever timed you on your multiplication facts to this day, except a teacher? What? No. Now, if you do it the way I tell you to do it, they're automatically going to get faster. It just works. But making them fast at the beginning just makes them anxious. And when they get anxious, they get nervous. And when they get nervous, they make mistakes. When they make mistakes, they get the wrong answer and their grade goes down. So they freak out. So we create a lot of math anxiety that's not really there. Now, You know as well as I do, females and males are different. I mean, females and males are just different. So my son, this happens a lot, not just boys, but boys tend to be, his goal was to turn the paper in first. In fact, none of it was right, it was just a sign. So I had to have a talk with him. You know, he's like, done. 42. But I turned it in first. You're like, no, baby, we can't, no. The goal is to be right, then we'll work on fast. But I'd rather than be right than be fast, okay? Now, let's talk about some models of subtraction. So that's the two main models in your book when they're talking about how do you teach kids to add, all right? And so, like I said, this number line model, you're eventually going to get to it. Now, I will tell you this. They'll do that sometimes. All right, let's talk about subtraction models. All right. Subtraction model. Can you guess what the first one's going to be? Sept model. It's totally concrete. Now, do you understand that with addition, you have two sets that you turn into one set? So you start with two. With subtractions, you start with one and you end up with one. Okay? So if you wanted to illustrate, say, 6 minus 4, I'm going to have a set on their desk with 16 in it. Now, it kind of goes to that idea of complement. I'm going to remove things from the set. Now, was the answer what you removed or what was left? What was your answer when you were doing complement? What's left? It's going to be the same thing here. Now, I'm going to have 6 Skittles on their desk. They are going to take away how many? 4. So they take 4 out, then they count how many are left, and their answer is how many are left. Now, again, you can't do that for me on a test because we're in a pandemic. So what you're going to do is this. You're going to show me that you're going to take these out. Is everybody with me? And then you're just going to show me that you have 2 left. Does that make sense? But now they're not drawing it. What are they doing? They're literally what? Taking it out. Now, remember how I told you that you teach as much by what you do and what you don't do? All right, here's what I mean by that. Why would this be a terrible example to start with?
Because you give the answer 3.
That's right. If I do this and they've got 6 things, and they take out 3 and they're left with 3, is everybody with me? I don't know whether they wrote down 3 because that's what they took out, or they wrote down 3 because that's what was left. So I've got to be careful. So here, if they write down the answer's 4, then they got confused that what they take out is the answer. So you've got to be real careful when you first start teaching, choosing your examples very carefully so that you can assess what they know and what they don't know. So again, that's what I would do first. I would do set model. All right, so they've got 7, they have to take out 5. They've got 7, they take all 7 out, they don't have anything. Okay? So set model. When they get really good at set model, you know what model I'm going to use next? Number line, that's right. Y'all are so smart. All right. So number line model. So again, my number line is going to start with 0. Micro cars come back out. Now, do you understand that it's very similar to what I did? What number am I going to start the car on? So the first number is still where I start. What's the difference? Which way do I go now? Left. So I've taught them that addition means you go to the right and subtraction means you go what? To the left. And then again, this second number tells you how many places you go. So I'm going to start at 6 and I'm going to go to the left. 1, what? 2. So that's where I stop. So my answer is, what am I doing? Oh, let's do 6 minus 4 since that's what we did. So that's where I stop. So my answer is going to be 2. And again, we go back and forth and back and forth and back and forth and back and forth. Now, let me show you another model that they use for subtraction. And then I'm going to show you kind of how I would do it. This one is very popular right now. I don't know why, but it is. It's fine, it's okay. It's called comparison model. So what they do on comparison model is this. It's kind of like addition. They give them 2 sets. Let's make it the same one, 6 minus 4. In other words, they have 6 of something. And then they have 4 of something. And then they pair them up in a 1-to-1 correspondence. So these are partners, these are partners, these are partners, and these are partners. How do they know what the answer is? The ones that are left. Kind of like over here, the ones that are left, the ones with no partner. Now, it's not my favorite, but it's all right. I don't know why it's suddenly super popular, but it is. Now, if I had to teach this, now how do you know when you have to teach something? You can look at your curriculum guide. Because if I'm the teacher and there's going to be a state test, and the state test I know has this on it, then I better what? I better teach it. Now, if the state test doesn't have this on there, I probably wouldn't. But if it does, now think about my 3 methods so far. This, if I had actual things, right with me, if I had actual pieces, this would be pretty close to that set model. So I might teach the set model, and then teach this, and then go to the what? To the number line. Because what I'm trying to do is I'm trying to go from concrete and then gradually do a mixture of a lot of concrete with a little abstract, and then do about half and half, and then do a lot of abstract with a little concrete, and then finally get to just abstract. Now, let me show you another model that's really pretty abstract. It's called the missing add-ins model. All right, missing add-ins model. Now, kids learn to add before they learn to subtract. So here's what they're talking about. 6 minus 4 is some answer. Well, some kids will do this in their head. What do I add to 4 to get what? 6. What do I add to 4 to get 6? 2. So if the answer is 2 here, that's the missing add-ins, then the answer here is what? 2. But do you see how much more abstract this one is? So you're going to move them from totally concrete to abstract. And a lot of them will, in their heads, do this. That's the way I do division. See, when you ask me what 12 divided by 3 is, in my head, you know what I'm doing? I'm saying, what do I multiply by 3 to get what? 12. That's a missing factor model with division. So these are kind of your main models. Now, they're not the only models for addition, and they're not the only models for subtraction. They're kind of the popular models right now. Now, you might say, well, I'm going to teach 6th grade. Well, that's awesome, but sometimes you get kids whose teacher just kept doing this, and they don't have any conceptual understanding of addition. So they're supposed to be adding 145 to 9,773 in your class, and they can't. And the reason they can't is they never learned the set model down here. So sometimes you have to take kids aside and go way down and fill in a hole that didn't get filled in at the beginning. So what I always say is you've got to teach the kids you have, not the ones you wished you had. So ideally, if you're the fourth grade teacher, they have a very good understanding of kindergarten, first, second, and third grade material. But in reality, what? They might not. Well, you can't just force them to start here when there's a big gap. They fail, they fall down. So what you have to do as part of your job is, I got to go back down here and figure out what you know and start there. Now, the fancy educational work for that is scaffolding. If you've ever seen people that paint houses, they kind of build this structure that they can climb up to paint. That structure is called scaffold. So you have to scaffold. So you're going to have to find out what your kids know, and you've got to start with what they know. The fact they're supposed to know more does not matter. They don't. And so you got to figure out what they know and then move them kind of to what they don't know. Okay? So that's kind of your models for addition and subtraction. All right. Let me kind of flip through. All right. I got to show you that one thing. And then I think, okay. Okay. We're good. All right, now, let me show you one definition, then we're going to talk about your text. Now, part of this is teaching you to read a math book. So in your books, I want you to turn to page 100. All right, turn to page 100. Math is different than other subjects in lots of ways. And one of the ways that math is different is we're very succinct. Okay? We don't have a lot of extra words that we don't need. So if you're reading a definition or a property or a rule, every word is important or it wouldn't be there. So look what it says. This is your definition of less than. Now, here's my thing. You need to learn this. That symbol is less than. That symbol is greater than. I need you to learn what they are. Okay. All right, so less than and greater than. Okay? Now, the book on page 100 gives a definition of less than. Look what it says. For any whole numbers A and B, A is less than B, and it tells you how to write it. If and only if there exists a natural number K such that A plus K equals B. Now, think about what they're saying. Do we agree that 2 is less than 5? Is that a true sentence? Then they're saying if that's true, do you understand that this is your A and this is your B? Then there's got to be some number that you can add to A to make it equal what? B. And what kind of number did it say it had to be? It had to be what kind of number? A natural number. See, think about it. Is there a number that you can add to 2 that will equal 5? What is it? It's 3. Now watch this. Is this true? 2 is less than 1. Is that right? It's not, is it? And here's why it's not right. Is there a number that you can add to 2 that will equal 1? -1, but that's not a what? Natural number. There's not a natural number that you can add to 2 to get what? 1. All right, is this true? 2 is less than 2. Is that right? 2 equals 2, doesn't it? Well, let me ask you this. Is there a number that you can add to 2 that would make it be 2? Now, what kind of number? That's not a natural number, that's a whole number. So see, that one word natural number changes everything. Now, if I've got kindergartners or first graders, that's a true fact, but that's pretty abstract. So if I'm the kindergarten teacher, I'm the first grade teacher, or really if I'm the college teacher, when you tell them something, it's got to be true for all time. So please do not tell them the fewer the digits, the smaller the number. That's not true. -12 has more digits than 6. But -12 is not bigger than what? 6. So do not tell them the more digits, the bigger the number, because that's not true for what? For all time. So what is going to be true for all time? If I'm 7 years old and I'm looking at a number line, how do I know which number is bigger? What would work all the time?
If it's on the right.
The further to the right. That's all you got to tell a kid. The further to the right, what? The bigger what? The number. Conversely, the further to the left, what? The smaller the number. See, that works for all time. It works when you throw in decimals. It works when you throw in fractions. It works when you throw in negative numbers. Now, what we're not going to do is do some ridiculous trick about a gator eating a number. If you do that, I will come get you. And here's why. I mean, I've heard 1,000 of pictures. You know, open the mouth toward the bigger number. But they can't tell you what those symbols are. Well, see, you never leave second grade, but they do. They don't know where to open the gator. Do you see what I'm saying? So that trick is going to fail them. As a matter of fact, one of my former students in this class, I may have told you this. At Father's Day, I got a message on Facebook, and she said, Dr. Dan, that gator trick failed them again. And she was behind somebody, and she had snapped a picture with her phone, and here's what the picture said. They had put that on the back of their ride. Now that's just sad. What does that say? My dad's less than your dad. Now what do they probably mean? Greater than. That's not what they said. So that gator trick, and she just laughed and laughed. So Katie said, that gator trick failed him again, Dr. Green. Like I told you. You don't be dissing your daddy later. Okay? So cute tricks eventually hurt them. So they need to know that that symbol has a name and it's less than. Just like that thing's called a dog, that's a tree. We call that 5. You know, I mean, every pictures have names. And so teach them the proper names of those pictures. Now, this is where your test material is going to stop for test 1. So your first test is a week from today. Okay? So let's discuss what that's going to mean. So that means it goes through this section 3, 2. Excuse me, 3, 3. In that, I'm going to ask you to do, I'm not going to ask you to add and subtract in different bases yet. All right? So what I am going to ask you to do, though, are the properties for addition and for multiplication. And I'll write this on Moodle. Okay? So you're going to kind of jump and get some properties out of section 3, 4. But those properties of whole numbers for addition and multiplication are going to be on there. I'm going to ask you about the models for addition and the models for subtraction. Okay? But I'm not gonna, later, after the test, well, actually next time, but we're gonna learn to add and subtract in different bases, including base 10. We're gonna learn scratch addition, so we're not gonna learn everything out of 3, 3, 3, 4 is not gonna be in there, just some things. But let's go back and review for a second. The very first thing we went over was problem solving. So you know I'm gonna ask you for Pollier's problem solving process. You know I'm gonna ask you what are some problem solving strategies. All right, so make sure you can do that. You had arithmetic and geometric sequences, like patterns. You know I'm gonna ask you to fill in some missing numbers in a pattern. Like on that pop test, I might ask you, what's the 155th term? You don't want to be adding 7 155 times. Is everybody with me? So you need to know those formulas for an arithmetic or a geometric sequence. Now, I'm going to give you some real problems, not exercises. You can't really study for that. But you're going to use those strategies. Drawing a picture might help. Writing an equation might help. Making a list might help. All right? So you're going to have some true problems out of that first chapter. All right? The next thing that we went over, we talked about sets. So all those definitions, like the definition of a subset and a proper subset, an element, not an element, disjoint sets. I'm going to give you sets and ask you to do me the union and the intersection and the complement, like on that worksheet. I'm going to give you sets and make you draw me a Venn diagram of them. I'm going to make you do a Venn diagram shading of some things. So all that stuff that deals with sets out of that chapter 2. And then chapter 3, you know, you got to be able to do Roman numerals to standard numbers and standard numbers back to Roman numerals. You've got to be able to write numbers in expanded form. You've got to be able to change from other bases to base 10 and base 10 back to other bases. You've got your properties, and then you've also got your models, your addition and subtraction models. So that's what's on your test. Now here's what's going to be a little strange. I can't get everybody, I can't get 30 of you in one room. So what's going to happen Tuesday of next week is the people sitting in front of me are going to be sitting in front of me. The people in Zoom are going to be in the lobby of MCC. Their cameras, and my secretary's got a giant screen that she watches people take tests on. So the lobby is going to be reserved on Tuesday at noon for the people that are on Zoom. Now all you can have with you is a little, you can have a calculator and a pencil, but you can't have a book bag or a phone. So if you're on Zoom and you have a class right before this or right after this, you're going to need to bring your book bag and put it down here with your phone and leave it in the room while you go to the lobby to take your test. And then you can come back and pick up your book bag. Same thing for y'all, you just got to be put up. Okay, now the next time we take a test on test 2, I'm going to make sure that's on a Thursday, so that those people are in here and that you're in the lobby. Okay, so that we make it fair. So part of your homework tonight is going to be this new stuff, but also to start studying for your test. Now, what's weird for y'all is I won't physically see you until you take your test. So what that means is you're going to have a worksheet on Moodle to finish and some things. You're not going to be able to ask me a question on Thursday. So if you have a question, you need to set up a meeting with me or email me. Okay, because the stuff that you have homework for tonight will be on your test next week. Okay, all right, I will see y'all on Zoom on Thursday, and I will see y'all when you take your test.